Welcome once again to this introduction to TDPnet. In this session, we will explain the fundamental problem that TDPnet aims to solve. Remember to register for the channel and kindly press the like button, hoping you find this content helpful. TDPnet is a special way of building and running computer systems, and it's based on solid math ideas. We're using three main areas of math. Category theory. This is about finding connections between different things. Abstract algebra. This helps us understand how parts of a system can work together. Functional analysis. This focuses on how things change over time and helps us measure those changes. These math ideas come together in a system called Maxwell mechanics. The goal of TDPnet is to create a system where we can look at what's happening in real time and make changes to keep everything working smoothly. By following math principles, especially one called the least action principle, we can make sure the system runs as efficiently as possible, using the least amount of resources to get things done. All the important ideas behind how TDPnet works are about its structure. Here's a list of the main 10 rules that guide how this network is built. First, like the internet, nobody owns TDPnet. Second, main parts. TDPnet is made up of three main parts: service providers, or SPs, edges, and bridges. Third, peer-to-peer network. TDPnet works like a peer-to-peer network where SPs act as the peers, or members. Each peer can connect with many others, and these connections happen using bridges. Fourth, bridges only. Peers need at least one bridge to connect to other peers. They can't connect directly to each other. Fifth, channels. The connections between peers are called channels. Think of them as special codes made of zeros and ones that show which bridges are used. Sixth, systems. A system is a group of at least two SPs that use the same rules, channels, and security. Edges help keep these SPs safe by separating them from the bridges. Seventh, at least one system. The network must have at least one system in it. Eighth, changing channels. The channels an SP uses can change, which makes the network safer because an SP can't tell where the other peers are just by looking at the channel. This means SPs only need to pay attention to who they're talking to, no matter where those other SPs are. Ninth, no limits. There's no limit to how many SPs, edges, and bridges the network can have. And last but not least, no special equipment needed. TDPnet doesn't need any specific type of hardware or existing rules to work. Here are the initial methods and tools we considered for developing TDPnet. These approaches are preliminary and will be reviewed and refined as needed. Methods. Building a normed Hilbert space. This is a mathematical framework used to represent the state of the TDPnet system, helping model how the system behaves. Training a wave function with machine learning, ML. Machine learning is used to train a wave function model. This model can predict how the TDPnet will behave and adapt to different scenarios. Using UDP as a communication protocol, the User Datagram Protocol, UDP, is chosen for building a prototype because it's fast and doesn't need a connection, making it good for initial testing. Defining system physics with axioms. The rules that govern how TDPnet works are formalized into a set of principles. This requires moving away from traditional ideas of space and dimensions, which is a core part of Maxwell mechanics. Tools. Shannon capacity formula. This tool helps calculate how much data an SP, service provider, can handle, which increases as more bridges are added. More bridges mean more SPs can be supported, and because data can be split and sent through multiple points, the network's overall signal becomes stronger and less affected by noise. Quantum mechanics with the Schrödinger equation. Using the matrix version of this equation helps adjust the large Hamiltonian matrix, which represents the energy states of the system. This lets engineers fine-tune how the network behaves and ensure it runs smoothly. Data redundancy and entanglement mechanisms. In TDPnet, bridges can split data packets into smaller pieces and send them through different paths. At the destination, quantum decoherence techniques help reassemble these packets correctly, ensuring that the data arrives intact and noise is minimized. You've made it this far, and we hope you find this technology as exciting as we do. Stay tuned for more videos where we'll explore the many facets of TDPnet in greater detail. Thank you for watching.